So good morning, everyone. If you hear me well, please say yes on the chat.
Yes.
Yep.
Okay, great. So today I will talk about surface transit punching. So I will start by a short intro. So as we all know, transit surface vehicle punching has been a problem that we have been facing for a long time. Punching refers to when two consecutive transit vehicles cannot really maintain the scheduled headway and they end up behind each other along the corridor, and it has many negative impacts on transit operators and in users. For operators, it means unused capacity, so every fully loaded vehicle will be followed by empty vehicle. For users, it will mean more crowding, more waiting time, more travel time, and less satisfaction of the service. We conducted two studies related to punching and specifically to streetcar punching. The first one focused on understanding the determinant of punching. The citation of this paper are here, and I think Professor Shalabi will share the slides afterwards, so you can really read this paper in more detail afterwards. For this study, we aimed to understand the factors that impact the odds of streetcar punching, also to determine the internal and external factors that impact the time to initial punching instant from the terminal. In order to achieve that, we used more than 6 million records from TTC vehicle location system for 8 streetcars in Toronto for 1 week from January 24th to 30 in 2016. DTC AVL system records vehicle location every 20 seconds. So punching instant were isolated at the segment level, where actual headway were less than half of the scheduled headway. So basically, we tracked the GPS point, and if the two last EVL point are within the half of the scheduled headway for the leading vehicle and following vehicle, that was a punching instant. And for each observation, data from the previous scheduled trip and from the one prior are used to better understand the punching phenomenon. So for each trip, we had also attached the information from two vehicles that are that are before them. So in our methodology, we focused on using descriptive statistics and visualizations to understand the trends of punching and where the punching happen along the routes. Also, we used two statistical models. The first model was binary logic model. I will not talk about these models in detail in these presentations, but you will find more details in the paper. So the binary logic model was used to understand the odds, the factor increasing the odds of punching. The second one, accelerated failure time model, was used to understand the factors that increase or decrease the time to the initial punching instant. And we used 3 types of variables in our model: control variables and internal and external variables. Control variables are related to, for example, to route number, time period of the day, weekday versus weekend. Internal factors are related to the factors that are within the control of transit agency, like scheduling, headway deviation, the mix of different type of streetcars, and also the use of transit signal priority system. External variable, it's related more to or less to the built environment and urban form, like number of pedestrian intersections, for example, number of signalized intersections also, and traffic volumes. So that's the first model, the binary logic model, and that's the second model. I will jump directly to the key results of this study. So first, longer schedule headways decrease the odds to punching and also delay the onset of punching. So basically moving to high capacity vehicles along the routes while offering the same exact capacity, line capacity, that will decrease the odds of punching. That's something that TTC now in process by implementing the Flexity streetcar, which is offer more capacity than ALRV and CLRV. And also regardless of the headway of adherence of leading vehicle at the terminal, when the following vehicle has an actual headway that is shorter than the scheduled headway, the odds of punching is increased. So it's very important to control streetcars at the terminal and make sure that they leave within the scheduled headway to decrease the odds of punching. Also, our model suggested that the odds of punching are higher in midday, PM peak, and evening periods compared to morning period. So that can also gain our attention while we understand and we want, while we are taking action against punching. Short turning is found also to be effective in reducing punching odds. So short turning is a common method used by transit supervisors at the TTC, where they redirect almost empty vehicles that are punched to provide revenue service in the other direction. And using this, it helps actually to reduce the punching odds. Also, important finding from this study that using different combination of vehicle types. So during our study, TTC was employing three types of vehicles, streetcars vehicles, the ALRV and CLRV, and the new one, the Flexity Outlook. And combining the three type of vehicles along route increased the auto punching and also accelerated the time to punching. So punching having more faster along the route. Also, we found that having different types of stop placement. Stop placement can be near side stop before the intersection or far side stop after the intersection or mid-way stop between the intersection. So having this mix of stops along the routes also increase the odds of punching and accelerate time to punching. The implementation of TSP in our study had a good and positive impact. So it delays the onset of punching, so it de-accelerates the time to the first punching instant. As mentioned, external factors like pedestrian crossing and signalized approaches have been found to actually accelerate the time to punching. When you have more pedestrian crossing around along the transit route, you expect accelerated time to punching, or punching will happen much more faster. Finally, one of the most interesting findings of this study that heavy traffic volume delays the onset of punching, and the opposite is correct. So dedicated right-of-ways will accelerate time to punching, and this is mainly reflected by when we have vehicles between streetcar vehicles. That will actually decrease or de-accelerate the time to punching instant. So based on this study, our second study focused on developing real-time prediction model for punching. The overall objective of the study was to develop a real-time model to predict the time from the instant the streetcar leaves its route terminal or any early stop along the route to the instant it first catch up with the leading vehicle. So in order to achieve this goal, we used EV, automatic vehicle location system data, and this time it was obtained from TTC Next Bus system for only one route, which is Route 506 Carlton, and this route had the most percentage of punching instant in our previous study, and we used data for whole 2 months, for March and April 2017. And then we conducted a comprehensive literature review to understand what are our options for modeling for real-time applications. And we decided to use Kalman filtering model, KF model, to two reasons. One of them, it offers more a generic model with explicit mathematical expression, which can be transferred across different routes with little bit of calibration. Also, it uses the observed travel time for the same trip in previous days of the same type, like weekdays or weekends. Also, and the observed travel time of leading trips on the route during the same day. So basically, it captured travel times from two sets, from previous days and also from previous trips during the same day. And this will help us to capture many factors that we can't really have information about in real time, such as passenger activity. And actually, this model provided us with good prediction quality, given it only relies on real-time ETL data. And this prediction quality improved if the transit vehicles travel away from terminals. So if we start our prediction at the second stop or fourth stop, the quality and the results will be more accurate in determining the punching instant. And also when we found that increasing the number of days that incorporated in our model beyond 6 days, or increasing the number of trips beyond 7 or 10 trips might increase the prediction error. So that's important information. So we don't need all this data to predict punching instant, and only we need like 6 days of data in ahead and 7 or to 10 trips during the day to do a more accurate prediction. Sorry. So finally, I would like to acknowledge Ontario Research Fund for funding this project, TTC for providing the data, also for the first project. For the second project, I would like to acknowledge INSERC Engage program for funding it, and CIMA Plus for partnering with us in this project. Thank you all. I will be happy to have any questions afterward. Thank you.
Thank you, Ehab. I don't see any questions, but as Willem said, please, if you have questions, you can put them in the chat. And over the course of the session, we're asking the presenters to answer in the chat room. But I will ask one question since there's none on the decks. You know, the departure, making sure the departures are on time is critical, and that's your research showed that. But you didn't really mention, and you mentioned short turns, but you didn't really mention holding mid-trip. Was there any findings about that? Whether that's how valuable that is or not?
Actually, the type of data we used, it didn't give us any information about holding, so we were not able to control it. Okay. We know that, of course, maybe some drivers take these actions by themselves without any instructions.
Slowing down, waiting for lights, stuff like that. Yeah.
Yeah. But it was hard to control without really knowing the current protocol in application in TTC.
That makes sense. Well, thank you very much.